that symmetry. We were in 1956, and by 1964 we found out that that was wrong too. And now I have to talk a little bit about those funny kaons, those quarks and antiquarks bound together that had turned up in experiments in the 1950s. By the 1960s, people could make beams of these things and study their properties. And when they studied their properties, it turned out that these particles, you can make them, but they only live for a very short amount of time. And they actually come in two different types. One of them is given the rather interesting name of K-short, and one of them is given the interesting name of K-long. What that means is that there seems to be a type of this fundamental particle which only lives for a very short amount of time. It lives for around about a billionth of a second and then disintegrates into a couple of other particles which we call pions. Its long-lived cousin lives for a long time, a real long time. It lives for about 50 billionths of a second. But when the long-lived cousin falls apart, it makes three of these pions. And what these ingenious guys did was that they made an experiment where they made a beam of kaons and they had both types over here. They let them go in this direction and they let them decay away. The short-lived guys decay very quickly. So if I were to walk all the way across here, and they actually walked about 30 metres away and stuck a detector over here to see what they had, all I should have over here will be the long-lived guys. So if I use my fancy detector to tell me what have I got here, I should only see things which fall apart to 3 pions. All the 2-pion guys died way over there. So they did their experiment and they found out, no, about 1 in 500 cases that they saw over here of the decays were the 2 pi types. So that didn't make sense. And the reason it didn't make sense was because it violated this fundamental idea that nature should respect this CP symmetry, this mirror symmetry and turning particles into antiparticles. Because basically that should say that these guys should only ever give you 2 pions, these guys should only ever give you 3 pions. Even though it's a little effect, 1 in 500, that's enough to show that nature doesn't respect this combined symmetry. And it turns out again that the way these funny little particles fall apart involves the weak force, and it's the weak force that's the problem again. Okay, all these exotic experiments. Now, where do our Kobayashi Maskawa come in? In 1973, so we're now about a decade after that really astonishing but rather exotic experiment was performed, they figured out that they could have a way in our fundamental standard model of nature. They found a way to put into the equations something which would allow for the weak force responsible for these types of effects to not respect charge parity symmetry. The details are rather technical, but in order to do it, it turns out that they realised that there had to be more types of quarks in nature than they were known at the time. Through the 1960s, people came up with the concept of quarks, but there were only 3 types, the up and the down that makes us, and another type called the strange quark. That was all that we had. Their theory required at least 3 different families of quarks. It required another one to go with the strange quark. Nowadays it goes by the name of the charm quark. Very interesting names that physicists come up with for these things. And some even heavier ones, which they called bottom and top. They didn't, but that's the names that they eventually got. If you're going to make a scientific theory that's going to explain something that we already see in nature, your theory is even better if it predicts something that has not yet been seen. And their prediction that there must be at least 3 families at that time was very radical, just like Dirac's idea that there must be anti-electrons. So one of the reasons that these guys are famous is because they introduced this idea in 1973, and by 1974 the charm quark had been discovered in high-energy physics experiments, followed by the bottom quark in 1977, and they had to work a lot harder to get the top quark, but it turned up around 1994. So they had a theory to explain something we already knew to be the case, and it predicted something that was soon seen. Okay, so that was part of why they became famous. This is all very exotic, isn't it? It's all very, these guys off in the laboratory at CERN banging things together, and what's profound about it? Well, it is profound to try to understand nature at its most fundamental level, but it also affects all of us, what's going on here. We believe the universe started in a Big Bang some 13.7 billion years ago, and it's evolved through various phases since then to give us something which we now see of great beauty when we look in the night sky. The galaxies, stars making up the galaxies, and so on. What we would like to understand is how the universe got from here to here. And our laws of physics ought to be able to help us understand that, the evolution of the universe. Okay? But there's a very interesting question that we can ask. The universe, as far as we can tell, is made entirely of matter. We're made entirely of matter. I'm not so sure about Paul, but we actually believe that the universe is made of matter. However, there's very good reasons to believe that when the Big Bang occurred, given the fact that matter and antimatter seems to be roughly equal and opposite, that equal amounts of matter and antimatter would be made in the Big Bang. So how do we get from a situation of equal amounts of matter and antimatter to a situation where something like the Andromeda galaxy and our galaxy is entirely made of matter? How can we understand that? Let's first of all ask ourselves the question, are we sure that everything out there is matter? Are there antimatter galaxies somewhere out there? We're reasonably sure. This is a beautiful image from the Hubble Space Telescope of 2 galaxies colliding. They're called the antenna galaxies. And there are many examples of these. If those galaxies were one matter and one antimatter, then the collisions between the stars in those galaxies would basically produce a lot of annihilations and a lot of energy in the form of gamma rays, very energetic quanta of light, if you like. But we'd never see lots of gamma rays coming from the regions of space where we see galaxies in collisions. This neat little animation here, for those of you that like to think ahead, is a simulation of what we think will happen to our galaxy, which was the galaxy at the bottom, and the Andromeda galaxy, which is moving towards us. Eventually, we believe those 2 galaxies will collide, and all of the mess that's come out there is the way that the stars will be thrown out. If that's going to give you a sleepless night, don't worry, it's going to happen in about 5 billion years' time. But there's no evidence that there are antimatter galaxies out there colliding with galaxies. I mentioned cosmic rays a little while ago, the idea that Dirac's famous anti-electron was discovered in cosmic rays. And indeed, what cosmic rays are cosmic messengers, such as protons, arriving from outer space, hitting the nitrogen atoms composing the air in the upper atmosphere, and causing a whole spray of particles to come raining down on the Earth, which we can detect with our Earth-based detectors, or indeed detectors flying in balloons. And from studying what actually arrives down here, we can figure out what those cosmic rays are, and it turns out that they are predominantly protons. We don't see a significant amount of antiprotons raining down on us, which again you might expect if wherever they're coming from, They're equally coming from antimatter parts of the universe as from matter parts of the universe. So the evidence coming from observing nature by looking up seems to suggest that the universe is indeed, as far as we can tell, made of matter and not antimatter. So this question of where did all the antimatter go is a big question. If there wasn't a mechanism to get rid of the antimatter, we wouldn't be here. The universe would just be bathed in a sea of photons. So the idea that people have arrived at is the following one.